Scheduling as a problem can be countered or managed through various mechanisms, which could be either one time or dynamic or period based. Similarly, scheduling can also be governed by certain strategies such as centralized, distributed, or uncoordinated. In this module, we should look at the most widely adopted scheduling in wireless networks, which is the centralized scheduling. We should look at the scheduling as a problem first. Then we'd look at the maximum capability of scheduling that a network can afford. Then we take the example of wireless single hop and multi-hop communication instance from Bluetooth technology. The references that I've chosen are Anurag Kumar and Kenneth Calvert, but you're also strongly encouraged to go through the books by William Stallings and by Haojing Wang. In these books, the topic of Bluetooth is especially covered at breadth. The problem of scheduling is basically allowing the sender-destination pair to communicate. The simultaneous activation of independent sets in a network is the scheduling problem, which needs some research and some brainstorming. The static link activation schedule is the one in which nodes are given a pre-order that they have to follow for the whole network lifetime. But a periodic link activation schedule needs continuous coordination and input by the current state of the network and the nodes. Let's assume that we have S independent sets, so we need to allocate a scheduling discipline that gives M, or the maximum number of slots, to these independent sets. The bandwidth allocation for, say, a certain flow E is given by summation for all the time slots for an independent variable I, which is divided by the total number of slots. So it means the slot allotment for the independent set divided by the total number of slots is going to determine the effective bandwidth availability for an independent set, say E. This takes us to understanding that if we were to allow each independent set, are we going to maximally occupy the overall network capacity? In an ideal case, yes. But in reality, the time it takes to arrange for the scheduling has a direct toll or offers redundancy. And that is why the overall effective network capacity is more than what time slots and bandwidths could be scheduled. For instance, if we look at flows, say lambda 1 and lambda 2 as two competing flows, and if, say, all the flows have an aggregate flow rate, lambda, which is bounded by convex or a closed area represented by the symbol. Here we see that the flow on each link would have to be less than the average link capacity under the schedule. And why is that? Because we are constrained. We can never exceed the overall link capacity, average link capacity of the whole network. So by and large, the link capacity allotment for each flow is going to be less than the average. Bluetooth, as an example, creates piconets and scaternets in a centralized time division multiplexing system. The master gives the clock and the frequency hopping sequence. And the master also determines which device gets to communicate with other device in either synchronous communication oriented manner or an asynchronous connection-less manner. So Bluetooth is a good example of how centralized scheduling is managed by the master and all the slaves abide by that.